Welcome to this video on banked curves. In this video, the main objective is to analyze the centripetal force acting on an object that is encountering a banked curve and to figure out an expression for the centripetal force to see what factors actually affect the amount of centripetal force needed to keep a car on a banked curve. The first thing I want to do is just take you back for a second to a flat curve. And remember, for a flat curve, that would be if there's no angle of incline here, that the centripetal force is going to be equal to a frictional force. And the frictional force we could calculate in a variety of different ways, but usually from the coefficient of friction times the normal force acting on the car. And that would give us the centripetal force acting on the car. So you'd see there that the centripetal force would be equal to the mass of the car times how fast it's going, divided by the radius of the turn. Now what we're going to say is that for a banked curve, all that means is we've now added an angle to the road. And this is actually a good thing, because if you think about it, if you're making a turn of a certain radius, the car has a certain mass, and you want to do that at a certain speed, you're going to need X amount of centripetal force. Well, sometimes the friction cannot provide that, because the coefficient of friction times the normal force might not be enough to provide that. In which case, you'd need to add some other force here, and this other force is going to help provide enough stability to make the turn at the speed that you want. So with a banked curve, what we are saying is the centripetal force is going to be equal to the frictional force plus some value of normal force. Now this is not a complete amount of normal force. It's not the total amount of normal force acting on the car, but just a component. Now if the car is neither sliding up nor down the ramp like this, what we're going to be able to do initially is eliminate friction. And we're going to say that the centripetal force is going to be equal to a component of the normal force. That will allow us to calculate an expression and figure out how much do all these factors, like the angle of the ramp, the mass of the car, the radius of the turn, and so forth, how do they affect the amount of normal force, or therefore centripetal force, needed to make the turn. So let's go over to this cross section of the ramp. That would be just cutting a slice out of the ramp. And what we're going to do here is draw a force diagram for the car on the ramp. Now go ahead and pause the video and try to draw that for yourself. Then when you come back, we'll take a look. Okay, so if you've had a chance to do this, you hopefully have seen that we have a weight force vector pointing straight down, and we have a normal force vector here pointing normal to the ramp, perpendicular to the ramp. Now the next thing we're going to do here is I'm going to tell you that we're not going to make the horizontal axis or the x-axis point along the ramp and the y-axis point perpendicular to the ramp. The reason being is that this is not an object sliding up and down the ramp. Right now we're saying it's fixed and it's just going around in a circle, so it's not moving up or down. Because of that, what I'm going to do here is I'm making some axes, and I'm going to leave my axes in the traditional form just like this. Now what I can see is that the direction of the centripetal force is towards the center of the circular path. That means that it lies exactly along what we're going to call here this horizontal axis. That means that the weight force is not contributing anything to the centripetal force, but this normal force vector falls between this horizontal and this vertical axis, meaning that the normal force has a component that points along the centripetal force and some of it that points not along the centripetal force. Now we're going to say that the curve is embanked a value of theta, and that this angle is congruent to this angle over here. So if you want to figure out the angle relationship between these two or prove that they're the same, you can, but that's not really necessary for this video. Now what I'm going to do here is I'm going to draw some components in. Here is a horizontal component of this normal force, and here's a vertical component of this normal force. Now, what I want you to do is figure out what is an expression using trigonometry to relate the components of the normal force to this angle theta. So pause the video and try to come up with an expression for the normal force along the centripetal force line and the normal force along this vertical line. All right, so if you had a chance to do that, you could see that the normal force along this short line over here is going to be equal to opposite of this angle and the normal force. So what I would say is that the normal force times the sine of the angle is equal to this component that falls along the horizontal. So I'm just going to write it as horizontal component over here. And the vertical component is going to be therefore n cosine of theta, because they'll always come in pairs. So what we can say here is write a net force statement for the centripetal force. Well, the centripetal force, the only force that lies along the line that points towards the center of the circle, is this n sine theta component. The vertical component, because this is not moving up or down the ramp, what I'm going to say here is that the weight force is actually equal to n cosine theta. Those two would be equivalent to one another now because of the way that the picture is drawn and the way that we've created the proportion. So what I'm going to do here is I'm going to come up with an expression that might be a little bit of magic to some people, but I can see here that if I take a ratio of these two equations, n sine theta over n cosine theta, what I find here is that I would have n times the tangent of theta. Now it's not really going to be n times the tangent of theta because this n should factor out, but we're going to do a couple other things here. We know that the centripetal force is equal to the mass times the speed over the radius of the turn, and in this case this is equal to m times g. So instead what I'm going to do is say that n sine theta over n cosine theta is equal to mv squared over r times mg, times 1 over mg. So all I've done is I've just written the ratio substituted in with these variables. But you can see that the mass of the car actually doesn't matter. This factors out, and I'm left, as we just saw, with tangent theta, and that's going to be equal to v squared over r times g. Now this is pretty cool because what it says is that the angle needed for the ramp depends on how much speed you want to achieve, and it determines the radius, and is determined by the radius of the path. So you can basically say that the angle that I need to have for my embankment can be equal to the inverse tangent of the speed squared that I want to achieve over the radius of the curvature times g. So these would be the factors that are involved in determining the angle of the ramp, if you want to look at it from that perspective. Now usually you can't adjust the angle of the ramp, so maybe you want to look at it from the perspective of what speed can I achieve if the radius of the turn is blank and the angle of the embankment is blank. You could then solve for v and determine a value for the speed that is achievable. Now the last thing I want to leave you with is think about if friction was involved. So let's say that the car started to move outwards. Well, that would imply that there would be friction pointing down the ramp like this. Or perhaps the car started to slow and moved inwards, then there would be friction pointing up this way. You can see that there's this optimal speed where no friction is needed in either direction, and that would allow me to calculate the centripetal force as n sine theta, or this perspective over here. That would be the ideal speed needed where there's no friction involved either way. If friction was involved in one way or the other here, we would have to factor that into the centripetal force, because you can see that this friction contributes to this vector direction. But I'll leave that for you because that's just a slight alteration of this topic.